ईयर स्टूडेंट्स, अगर आप इन वीडियो लेक्चर्स का मैक्सिमम यूटिलाइजेशन करना चाहते हो तो आई थिंक आपको ये इंप्रूव सेशन डेफिनेटली फॉलो करना चाहिए और रिलीजियसली फॉलो करना चाहिए। इंप्रूव सेशन क्या है, इसका लिंक डिस्क्रिप्शन बॉक्स में है, तो जाओ उसको चेक करो। इसके अलावा अगर आप व्हाट्सएप ग्रुप ज्वाइन करना चाहते हो, और मुझे लगता है आपको करना भी चाहिए, तो आप क्या करो, हमारे वेबसाइट पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो या फिर इस व्हाट्सएप नंबर पे जाकर के अपने कॉन्टैक्ट डिटेल्स दे दो, सो दैट हम आपको उसमें ऐड कर सके। चलो अब पढ़ना शुरू करते हैं।
Hi, welcome back. In this video we'll be doing the left out topics. This is law of conservation of energy, and the second part of it is going to be conservation of mechanical energy, and the last topic, problems involving chain. So let's start with this one. So we have this formula, work net is delta K, that means total work done by all the forces on the system is basically the change in kinetic energy, and this is your work energy theorem. Okay, so this work net can be divided into two parts. One part is going to be work conservative plus work other. So this work other is going to include all kind of non-conservative forces. So work other, this WC won't be there. So work other is going to include everything except the non-conservative, except the conservative force. So it's going to include the non-conservatives, the external, the internal. So anything that is not conservative, I'm going to put it in work other part. And suppose in a given system the only force that is doing work is your work conservative and everything else is not doing any kind of work. So in that case work other is going to be 0, and then I'm going to write WC or work conservative is delta K. And we also have this formula, from the definition of potential energy we discussed in the previous video, and WC work conservative is minus of delta U. So I'm just going to put it here, and work conservative, this becomes left hand side becomes minus of delta U, right hand side is delta K, so this becomes delta K plus delta U goes to 0. Okay, so now delta K can be written as KF minus KI, and then delta U can be written as PEF minus PEI, and again this can be rearranged in this form: KF plus PEF is equal to KI plus PEI, and KF plus PEF or just KE plus PE is defined as the mechanical energy of the system. So what we have here, that total energy, total mechanical energy final is equal to total mechanical energy initial. So TF is equal to TI. So this is a direct result of saying if only conservative force field is doing work, the total mechanical energy of the system remains constant or conserved. Okay, so we'll discuss this whole calculation in with a given example. Just wait for a moment, and let me be very clear. So whenever you are solving some pulley related problems, so if there is a string in that and some string constant or constraint relation is there, so what we have in this in that scenario, that work done by tension on the system is always going to be 0. Why? So suppose we have a given string. Okay, this is a random string, and this is just a string diagram. What do I mean by string string diagram? So in this case string is going from here to here. So if I'm just talking about the string diagram is going to look like this, or maybe in this case it's going to look like this. So I'm just showing the part of the string, and every part of the string during the motion is going to be taut. Okay, so it's always taut. What do we have in the case of string, that if the string is going to be ideal string, that means it's non-extensible and massless. What the relation that we have, that every point on the string, be it the end points, be it the middle point, every point on the string is moving with the same speed along the string. I'm not saying same speed like the net same speed. Okay, so they are moving with the same speed along the string. Now think about this general straight string. Okay, if the string is inextensible, every point on the string must be moving with the same speed along the string, right? So that's why it's inextensible. So we can use the same equation here, and if in that case, suppose here we have a general string, so if this point is A and this point is B, and this whole system, this A is moving towards left, again this B must be moving towards left. At point A the tension is going to be rightward, at point B the tension is going to be leftward. So work done by tension T dx, work done by tension here is negative, and here is going to be T dx positive. Why I'm taking dx, because every point on the string must be having the same displacement along the string. So if tension is acting like this, along the string direction is just opposite to tension. Dx, again tension is like this, along the string direction is just the direction of tension. So that's why I'm taking dx here, and this tdx is positive and this tdx is negative. Work done is negative, work done is positive. Pause this video and try to let it sink why that's the case. Okay, so here the total work done on the system by the string. So if I have a particle attached here and a particle attached here, so this constitutes the system work done by tension on both the guys is going to be 0. But if I'm talking about the individual work done, that means work done on this guy is going to be non-zero, that is minus tdx. Work done by tension on this guy is going to be tdx, again non-zero, but for the whole system is going to be 0. Okay, so we'll use this concept, conservation of mechanical energy, and calculation of potential energy in general case, so to solve the problems involving chain. So let's go to the next topic. Okay, let's discuss the problem involving chain. So here we have a uniform chain of mass per unit length lambda, and total length of this this chain is L, and suppose it's kept on a table with h length of the chain hanging below the table, and L minus h is on the table. Okay, so first of all, if I'm going to calculate the potential energy of this chain in this scenario, I'll have to define my reference line. Okay, so reference line is basically the line or the surface at which my potential energy is going to be 0. So it's defined in a general case for which if I'm going to go above that surface or above that line, my potential is going to be positive, and below that line the potential is going to be negative. I have discussed about it in the previous video. See to it to understand. Okay, so here in this case, if this is my p is equal to 0 line, so this part, that L minus h part, this is on the same line, so on the same surface, this is going to have a p component 0, so this is not going to have any potential energy in this reference frame. Okay, and potential energy is going to be acquired by this h length. Okay, so what I'm going to do, I'll just redraw it, and suppose this is my h length. Okay, I'm going to take a differential element dx. Okay, dx length, and that is going to have a mass of dm is going to be mass per unit length into the length. So mass per unit length is lambda and length is dx, and I'm measuring every distance from this point. So this is my origin. Okay, so origin, and I'm taking downward positive. So this part, this dm is a positive number, again my dx is also a positive number. Okay, so this dm is lambda dx. What is the potential energy of this dm mass? It's going to be minus dm into g into x. Why? Because I'm going below that surface, and if I'm going below, and this is already 0, so this potential energy, anything below is going to be negative, and this guy is at a distance of x from the table. So this dpe, differential potential energy, is going to be minus dm into g into x. Okay, now what is the value of dm? Dm is lambda dx g into x. So dm is lambda dx and then g into x. Again, this is your dpe. Now talking about the total potential energy is basically integration of dpe, and integration of dp is minus lambda g x dx, integration going from 0 to h. So this is going to be lambda g h square by 2. Okay, so this is very easy. This is the potential energy, gravitational potential energy of the chain in this scenario. Okay, now in many cases this lambda value won't be given. They are just going to mention that the total mass of the chain is suppose m, and total length of the chain is L, and some fraction of it is hanging down. So they are going to say something like L by suppose 3. So in general they are going to say L by n is hanging out. Okay, so in this case the potential energy PEG is going to be minus lambda is going to be mass per unit length m by L into g again, and g by 2, and this is going to be h square. H square is basically the height of the string that is hanging down, or and in this in that case it's going to be either L by n, where n can vary. Suppose in specific case they're going to write L by 3, so that is going to be L square by 9. Okay, so I'm just going to take the general case, and this is going to be h square. This is your h is L by n, so L square by n square. So this will converge to minus mgl by 2n square. Okay, so this is the general form if total mass and the total length of the chain is given. This is your n. Okay, so let's move on to how they're going to frame different kind of problem using this chain. So one method or one problem is like they're going to say how much work is going to be done if I'm going to put this chain back on the table, like the whole chain. So in that case you're going to calculate work done by the external agent to move this whole lower chain back on the table without giving it any kind of kinetic energy. The other part is going something like they're going to say suppose this surface is smooth, and then again nu is going to be 0, and then if I'm going to release this chain at t is equal to 0, what will be the kinetic energy of the chain when whole of the this whole chain is going to leave the table. So in that case, and the boundary scenario or the final scenario is going to be the last part of the string has just left the p is equal to 0 surface. In that case they are going to say ki what will be the k of the chain. Now the third kind of problem might be this variation of nu. So in this case it will be given this nu is not equal to 0, so there is some definite nu, and in that case again they are going to ask what will be the k of the chain when this whole chain is going to leave the surface. So if there is no friction, obviously there won't be any work done by friction, so only gravitational force is going to do work, and in that case conservation of mechanical energy theorem will hold good. And if there is non-zero friction, so friction will be doing some work, and that friction work done is non-conservative in nature. It will dissipate the total mechanical energy system, so that we have to include that part as well. So in that case we cannot use conservation of mechanical energy. We are going to use work done by all the forces. Gravitational force plus work done by frictional force is going to be delta of Ke. And keep in mind this work done by gravitation is going to be positive because the chain is going down and force is also downward, and work done by friction will be negative. Okay, so this will positive and this is going to negative because chain is going forward while the friction is going to act backward, and again delta K. So in the coming sections we'll discuss how to do those kind of problems as well. Okay.